Hello, in this video we're going to talk about topic 4.3 of AP Chemistry's curriculum, representations of reactions. And when we're talking about representation of reactions, of course we can represent reactions in a symbolic form like in a chemical equation. So if I wrote H2 gas plus O2 gas produced H2O gas and I balanced it, H2O gas, and I balanced this, you have a pretty good understanding of what this means since you've gone through AP Chemistry. But we could also represent this on more of a symbolic level where the H2 is represented by circles and the O2s are represented by circles. In other words, modeling these in ways that represent what the atoms are doing and how they're bonding together. Because this right here is very abstract. But what if we could make it look a little more concrete? For instance, H2. We could represent an atom using just a circle. And so if we draw a circle, then that would represent an atom. And if we drew like a solid circle, that could represent a different atom. And then if I put the circles together and I made them touch one another, then that could represent a molecule because molecules are just atoms that are bonded together. So how could we represent this particular equation? Well, let's say that we used the clear circles to represent hydrogens. So to represent a hydrogen molecule, we would represent that with two clear circles touching one another. And so that would represent an H2. Now we have a coefficient of 2 out in front, so what would we do to this to represent that coefficient of 2? Well, that means we have two separate H2 molecules. So I would draw another H2 molecule, not touching the other H2 molecule, and now we have two separate H2 molecules. This is a nice way to represent those two separate H2 molecules. Here we have an O2. So let's say for O's we use a solid circle. So this would represent one atom of O. But since this says there's two oxygens bonded, then I could represent that with another solid circle bonded to it. So that would represent one molecule of O2. And since the coefficient is 1 here, I'm just going to draw one O2. Then these become H2Os. Now, in order for H2O to exist, these atoms have to all break up from one another and reorganize themselves into water molecules. So how would we represent a water molecule? Well, O could be represented with that solid circle like earlier. And then the two H's are bonded to it, and those would be represented with the two clear circles bonded to it. So that would be a water molecule. One oxygen, two hydrogens bonded to it. The coefficient 2 in front means that I have two independent water molecules. So I have another water molecule, which also has the two hydrogens and one oxygen. So if you'll notice here, we have now represented all of these molecules from the symbolic form of the chemical equation to a more pictorial form of hydrogen and oxygen atoms rearranging themselves. Notice the law of conservation of energy, mass is followed. We have 4 independent hydrogen atoms here, and we still have 4 hydrogen atoms over here. We have 2 oxygen atoms right here, and we still have 2 oxygen atoms over here. So this also represents the law of conservation of mass, because the number of atoms we started with is the same as the number of atoms we ended with. So let's try another one of these. Let's say that we have some N2 molecules, and let's represent N2s like this. And let's say we also have some H2 molecules. And let's represent H2 this time with the solid circles. Okay, so let's say we have this, and let's say we have a few nitrogen molecules. So we have 3 nitrogen molecules, and let's say we have 3 hydrogen molecules. And we have a reaction that produces NH3. So given this many molecules of nitrogen and this many molecules of hydrogen, how many molecules of NH3 could I produce, and what would be left over? So again, we're looking at a symbolic way of doing this. Well, we have 1 nitrogen bonded to 3 hydrogens. That means we could split this nitrogen here, and that would give us 2 nitrogen molecules, and it could bond to 3 of these hydrogen atoms. So we'd split up one of these hydrogens, split up another hydrogen, and that would give us 3 independent hydrogens to bond to a nitrogen. So one nitrogen bonded to 3 hydrogens, 1, 2, 3, and that would take care of one of these nitrogens and 3 of these hydrogens. So we do it again because we still have some more hydrogens, we still have some more nitrogen. So another nitrogen molecule, the second one that was split apart here, can bond to 3 more hydrogen atoms, and we get another ammonia molecule. But if you'll notice, we've used 6 hydrogen atoms, and there are only 6 hydrogen atoms. So we have no more hydrogen atoms to bond here. So what's going to happen to these other 2 nitrogen molecules? Well, hopefully you realize that they are the excess reagent, and they just stay like they are. So this would be a nice representation of when 3 nitrogen molecules and 3 hydrogen molecules are allowed to react with one another, what would be produced? And again, following the law of conservation of mass, once we run out of hydrogens, no more nitrogens can react, but we still need to follow the law of conservation of mass. So the 4 nitrogen atoms that didn't react, they just stay exactly like they were as 2 nitrogen molecules. So this particular topic, representations of reactions, is just looking at how can we represent reactions pictorially, and how can we account for atoms using the law of conservation of mass. So that's topic 4.3. If you have any questions about this, please let me know. Good luck.